Hello and welcome to Microfile. Now, how powerful is an Amiga, a BBC Micro? And what is power anyway? Is it in the hardware or the software? If you're considering buying a computer, one of the first things a salesman is likely to do is to quote from the PCW benchmarks, and these tell you how fast the machine is. So, if you never really understood what a benchmark was testing, this one's for you.
John Cole, what are benchmarks?
Well, benchmarks are just computer programs, like this one, which you can run on a range of different computers. This one's just a few lines of BASIC. It's a basic benchmark. And all it does is print an S, set K to 0, add 1 to K, and if K is less than 1,000, then it goes round again. So quite
it's
simple.
Just counting to 1,000, in fact. But I noticed straight away that you could easily speed that up. For example, these could be integer variables, you could lose the go-to, you could put multiple commands on one line and so on.
Well, put the go-to in, especially for you, of course.
Oh, thank you.
Yeah, but the point is, if you changed the program and optimised it for each computer, we'd really be testing your ability to write a good program. And we don't want to test that. What we want to do is to test how well the computer works. So we use exactly the same program, with all its deficiencies, as you rightly say, on all the machines. That way we compare the machines, not you.
So it's a shoddy program. Who wrote it?
Thanks. Well, I put these benchmarks together back in '77. Actually, I pinched most of them from another magazine.
It all comes out now.
Anyway, yes.
So you did all those PCW benchmarks, or you collected them?
Yes.
Right. Well, let's see this one in all its glory running.
Right, I have a stopwatch here. If I can hold it very still and type run and start the watch together, we'll see how long this one takes. Wait for the E, stop, and that's about 2.7 seconds.
Right. Now, first question, obviously, why are you using a stopwatch when there's an internal clock?
Well, there's an internal clock on this machine, but there isn't on other machines, and particularly when we wrote this thing, there weren't internal clocks on any of them. If you want the program to run on all the machines, you can't afford to use a clock. So this program, as is, will run on lots of machines.
But a stopwatch isn't terribly accurate, is it?
Certainly not the way I did it just then, no. But no, it isn't. But actually, if you're timing... This one's only 2.7 and stopwatch isn't very good. Normally, you're timing longer things and it's OK. But even with this one, if you run it 3 or 4 times, it's OK.
So there are many other benchmarks?
Yes, there are. I've got a more complicated one here. Another one in the series, benchmark 7. This has got some of the same elements. K equals 0. From the old program, and if K is less than 1,000, that's from the previous program. But there are other lines in, like this one here, dim M5, that's dimensioning an array. There's some really wild arithmetic here. A equals K divided by 2 times 3 plus 4 minus 5. You know,
higher mathematics.
Pretty stretching stuff. And a go sub here, go sub 230, which just does a return.
All the usual things you might want to do in BASIC.
Right.
I see. But of course, there's nothing like the procedures that are exclusively BBC Micro.
Exactly.
I do notice this, though. This is BBC Basic, isn't it? Colour 129, sound 1, minus 15,
The producer, God bless him, insisted that we put that in, turn the screen red. So we've got a specific line in each of these machines. Now, we've actually got 4 machines here. At the far end, we've got a Commodore Amiga with a program in, and we've got a Sinclair Spectrum Plus, and we've got an Atari 520 ST, and here we've got a BBC Master System. They've all got the same program in. We'd like to run them. I think if we get Lesley, come on in on that one, please, and Mac on the Spectrum.
Should point out that's a Spectrum 128, not the Spectrum Plus. There is a difference. OK, are we ready? 3.
No.
We're not.
No.
We're
Yes,
live.
I am now.
3, 2, 1, go.
Right.
Now, mine hasn't run. My function key has collapsed on me, which just goes to prove it is live. Now, at the moment, we've got 4 different micros. They've got 4 different processors. Obviously, we're going to get quite a span.
Amiga's gone. Amiga's gone.
How long was that?
And it was 14 seconds, Fred.
Right, well, I happen to know that this one would have been, if I got it right, it would have been 17 seconds.
And in rehearsals, this one did it in 21 and a squirt seconds as well.
What's it done now?
22.
Right, OK. So what about you, Mac? How are you getting on?
Spectrum very reliably, calculating it on very deliberately. It's going to win in the end.
In the end.
Tortoise.
Right, excellent. So, look, why did the Amiga win? Was that because it's a 16-bit?
Well, the benchmark tests various things. Yes, it's 16-bit, but really what it tests is how good the basic interpreter is, or that's another factor. And in many ways, that's testing how good the programmer was who wrote the basic interpreter.
Right.
So it's really testing several factors.
But there's a whole lot of things it's not testing at all.
Exactly. Now, the dear old Spectrum is a bit slow on this benchmark, but it's got some darn good graphics, and you get
Yes,
some assembly
yes.
language games which are first rate. So it doesn't test the graphics, it doesn't test the disk drives, how good the keyboard is, what the value for money is. All those things are missed out on this benchmark. You've got other benchmarks for those things.
Of course, it would be possible to put it together on micro.
There goes the spectrum.
Ah, excellent.
77 seconds.
77
Reliably, I
seconds.
might assure you.
Right. Well, actually, that is a bit faster. That we're actually operating that in 48K mode, because we discovered earlier today that if you run that in 128 mode, it takes, I think, 107 seconds, which is about 30-odd% slower than that. Very strange. It would be possible, wouldn't it, to put together a micro which just performed well on benchmarks and nothing else?
Yes, it wouldn't be much good for that. The other thing you can do is to choose your benchmarks very carefully by each machine. So when you're promoting a particular machine, you show off the benchmarks that it works very well at. And that's something we see repeatedly in the magazines, of course.
So does that mean we're not really to take them too seriously?
Yes, very much so. Just one more factor, to consider, but don't take them too seriously.
So which of all the benchmarks is the best one?
Well, Max said to me during rehearsals, very good advice. It's really to run the program that you actually want to run in real life. That's the best benchmark on the whole thing.
Right.
One of the major advantages of the newer, more powerful machines is their much quoted ease of use. No longer do you have to have a lot of technical know-how to be able to use them. Switch on most computers for the first time and chances are you'd see little more than a collection of meaningless messages and a flashing cursor. But now you can have a WIMP instead, as Fred found out when he reviewed the new Commodore Amiga.
WIMP actually is an easy way of using a computer without typing in all the usual codes and incantations. In fact, for a lot of uses, you can forget about the keyboard altogether. WIMP, W-I-M-P, stands for Windows, Icons, Mouse and Pull-Down Menu. Right, well, what's all that about? This is the mouse. It's a rollerball device, as you can see. As I move it around on the desktop, I'm also moving this arrow around on the screen. Right, that's the mouse. Now pull-down menus. A few of those up here. There's one, another, and a third. Now this is another alternative to typing in. So, for example, if I want to enter the word redraw, instead of keying it in, I simply point to it and select. Windows are these things here, the boxes on the screen. Now you can think of those as sheets of paper on a desk. Using the mouse, I can swap them over. I can move them about. Let's put that one in the front again. Move it down. And I can even change the size if I want to. And icons are these images here, these symbols which represent the programs you might want to select. So let's load up the demos file. Right, I move the mouse to it and press a button, and straight away up comes another window and some more icons, each of which is a program that I might run. Well, firstly, I'll kill off this window here and tidy up the screen a bit. Get a shot of that. Move this to the top. Now, ready to load something up. I'll try this program here, which is called Lines. Once again, move to it, click the button, and up it comes. This is a graphics demonstration, so it really needs to be big. So simplicity itself to move to the top, stretch the window, and there it is. And that gives you some idea of what the WIMP philosophy offers. But so far, this hasn't done anything that you might not have seen on other machines. This, though, is the new Commodore Amiga, and it can do a lot more than the micros you may be used to. And to show that, well, let's try another demonstration here, this boxes demo. There, I'll stretch that one again, move it to the top, make it a bit bigger. Now, you'll notice that the Lines program carries on running. And in fact, all the time I've been speaking, down here, hiding away, is yet another program. This is another nice facility, being able to bring this screen on. So you see, we've got 3 programs going there. This, you see, is a multitasking machine. Each of these programs gets a share of the computer's time. The computer switches from the Lines program to the Boxes program to the Triangles program thousands of times every second. Well, of course, the more programs you run, the slower each one gets. Look how jerkily that Triangles program is moving. But if I remove some of these others here, kill that off, kill that and that, watch what happens to the speed. Those triangles are drawing much quicker now. It's got the processor all to itself, so the program can run faster. Well, you may be wondering how the Amiga gets this sort of speed. In fact, it's got a 32-bit microprocessor, and that means it works on chunks of data 4 times the size of conventional 8-bit machines, and it uses modern chips which are faster anyway. Here's the motherboard from inside, and this is the 32-bit microprocessor. The smart design doesn't stop there, though. Here are some custom chips, specially designed chips. These two here handle the graphics and the animation, and this one handles just the sound. So the processor doesn't have to do all the thinking for the machine. It can delegate certain specialist tasks while it gets on with other things. And there's another advantage that comes from using these custom chips. They can pack a lot of functions into a single integrated circuit. And the result is a computer with very few components, which is cheaper to make and more difficult to copy. Now, the graphics chip will generate over 4,000 colours on screen at the same time, as you can see here. Although in normal use, you'll have to make do with just 32, I'm afraid. But you can get some pretty snazzy animation, as we've set up over here. This they call Robo City. Now, if you wanted a complicated animation like this on a conventional micro, firstly, you'd have to compromise on the colours. But you'd also have to get the software to manipulate those characters, remembering, say, that the old man here moves behind the fire hydrant, but in front of the female robot, and so on. The Amiga has dedicated hardware, those custom chips, to look after the drawing and the redrawing, replacing the background and so on. Right, well, much as I like that demo, I'll pull that one down and move on to the sound, because sound is normally the forgotten feature of a micro. Traditional sound chips give you a rather crude quality. But with custom-built chips, you can get quality like this. I find that pretty stunning. That is actually stereo sound, and it's a sign of how seriously they take the sound facilities of this machine, that you can get more sounds by loading in directly the digitized sound files from the Fairlight, one of the most sophisticated of the professional computer musical instruments. If you don't fancy the old strings touch, what about this one? Heavy, man. It's also got text-to-speech facility, which you may remember we demonstrated in our review of speech chips in Program 1. Well, all this is fine, but what's it going to be used for? Well, multitasking has real uses. You can leave the machine to get on with, say, printing a long document at the same time as word processing and while the computer's sorting out some records on your database. But there does seem to be some confusion as to who this machine is aimed at. In the States, it's marketed as a home micro at about $1,500. Well, bigger disposable incomes, of course, over there. But in the UK, they're planning to launch it as a small business machine, which perhaps means that some of the facilities, such as this, are just not going to be used. Of course, any machine lives or dies by its software. There is an IBM emulation package for the Amiga, giving business users access to at least the top 25 IBM PC programs. But it takes time for software houses to learn the tricks of a new machine. In the meantime, you might make do with something like this. It's a graphics package which I'm not going to attempt to work myself. It's being worked live from upstairs in the gallery. It'll move about images, it'll distort them, it'll do anything you want it to do virtually, and it gives facilities which you would normally get only on dedicated graphics systems. No wonder it got a standing ovation at the Writers' Conference this week.
Pretty snazzy graphics there from the Commodore Amiga, which heralded a new era in powerful home computing when it was launched in the US in July '85. But power isn't just about hardware, it's the software as well, with better programming languages and techniques which take us further down the road to what might be called artificial intelligence. FREF investigated advances in computer vision, which will aid robotic investigation of dangerous areas such as 3 Mile Island.
People in the borough of Middletown. There has been an accident at 3 Mile Island. All pregnant women and preschool children should evacuate out of a 5-mile radius.
3 Mile Island, scene of the world's worst nuclear accident. 6 years ago, the core of this reactor overheated and began to melt. It took only minutes for the core to be damaged, but the reactor will take a decade to be cleaned up. Some of the interior is still so radioactive that only machines can survive there. A lot of money has been spent on producing robot vehicles which can move around under remote control. The ultimate aim is for them to be able to navigate on their own, identify objects, and do useful work, using artificial intelligence to decide what to do. This machine is being lowered into one of the worst areas, the lower containment vessel, where the floodwater is radioactive. The vehicle just setting off to explore was one of a number developed at nearby Carnegie Mellon University in Pittsburgh. A park keeper's delight, this one keeps off the grass and stays on the path using a video camera to scan the ground ahead. Computers analyze the scene, looking for parallel lines in the machine's plane of movement. The microcomputers on board control the steering, keeping it on the path without human intervention. Because the full analysis of what it sees requires a mainframe computer to do the calculations, it must relay its pictures back by radio. From its camera, it captures a series of digitized, high-contrast images and analyzes them, looking for features, in this case, parallel lines. It then looks for changes between one image and the next, and it is those changes which make it adjust its steering. Professor Red Whitaker is in charge of the project.
But there are lots of parallel lines in the world. How does it keep them separate?
Well, in this case, it's given some cues, specifically that it looks for lines which are parallel, evenly spaced, lines that are long. And using that criterion, it could, for instance, tell the difference between a road edge and a blade of grass.
Does it ever make mistakes?
Well, certainly. Our worst foul-up, which was that this machine was following this path that we're sitting on now and traveling in that direction. It looked into the scene, took a look at a tree, and interpreted in the following way: a pair of parallel edges that are long, that are straight, that will cast into its scene as an excellent road model. And it decided that that looked better than the path, took the tree, climbed the tree, and that was the end of that particular one. But in fact, the foul-ups are as common as the successes.
But the responsibility of letting this powerful machine loose in the real world in its present simple-minded state is a heavy one, especially for academics used to the safety of the laboratory. How would you like to meet one of these on a dark night? The inside of 3 Mile Island is a hostile one for any machine. Highly radioactive water scoured out the containment building and has left a lethal scum. Radiation levels here would be enough to give a man a lethal dose. Prolonged exposure is enough to burn out a video camera and affect circuitry on equipment which isn't properly shielded. On this unique film, we are seeing what Red Whitaker's machine saw last year inside 3 Mile Island as it moved down the now deserted corridors. A different approach to automatic navigation is being tried out back in the less hazardous corridors of Carnegie Mellon University. Instead of using vision to find its way about, this robot uses sonar, in other words, high-frequency sound waves, which are reflected back from objects in its path.
I gather that robot in the hallway has a name.
Yes, we call him Lurch.
Lurch scans the corridor using a ring of ultrasonic sensors, and you can see on the screen a representation of how it moves forward. The 3 parallel lines show its proposed path. As it sweeps around, it's plotting the position of walls and other objects and measuring its distance from them. If there is nothing in its way, it moves forward.
Sonar is good because it immediately tells you things about your environment. It tells you where you can and cannot go. So the information is immediately useful. A robot using sonar doesn't have to bump into anything because it always knows how far things are away from it.
Okay, what does it not do so well?
Well, it has a couple problems. Obviously, it sees at this level. It won't see things down here, and it won't see things up in the air. So it's possible for the robot to bump into something that it hasn't seen. It also gets fooled by things like the metal door outside our lab. Actually behaves like a mirror, just as people would be fooled by a room full of mirrors. Sonar can be fooled when the beams reflect off
by an acoustic mirror.
Exactly.
Well, it's all well and good to use sonar to build up a picture of the walls of a room so that the robot doesn't run into them. But what happens when the robot's in the room and has to do useful work? Sonar's not good enough. How could sonar pick up this cup in the midst of all these objects and interpret what it was? You've got to use some kind of computer vision instead, and that's a much, much more difficult task. This device is being used to test an alternative approach to computer vision. It starts here, where an infrared laser diode creates a point of light, which is spread into a line by this half-cylindrical mirror. The line scans across the object and is picked up by this lens. The computer knows what angle the lens is at, what angle the light's at, and is continually triangulating as it scans along the object. It does this several times, from different angles, and builds up a three-dimensional picture from its two-dimensional data. This is what the computer sees. Jerry Agan has been working on this problem for 15 years. Jerry, how does the computer sort anything meaningful out of that jumble of white lines?
Well, the idea is to build up a model in terms of features. For example, if it were looking for a flat surface, it would take a scan across in this direction, say like so, and then it would orient itself, say like this, and take another scan in a perpendicular direction. So if from two consecutive scans it finds that the surface is flat, it knows that there's a flat plane at that point.
And what does it do with that information?
Okay, that information isn't sufficient to tell, say, the difference between this and this, because they both have flat planes. So it has to go out and find more features. For example, edges, cylindrical surfaces. It would then have to go in and say, if it might be this, and if it might be this, where should I look in order to be able to tell the difference? So it has to it'll actually go out and
search
looking
for
that loop. Yes,
I understand.
And that will distinguish.
Of course, there's yet a further level of difficulty to the problem. Once you've gotten into the room and identified what's there, you have to deal with it in some way.
Now that's a big problem, right, Hans?
It involves integrating sensors, motion coordination, servoing to the actual manipulation. We're working on a time scale roughly 2 or 3 years on a problem that should enable one of our robots in that time to do the following. Identify a door visually.
Step one.
Servo towards the door. This is a navigation problem. With an arm extended.
Which is an engineering problem.
Yes, well, we are at the moment going to be working with a rather specialized arm, but the idea is that eventually we go to other things as well. Robot approaches door, servos hand onto doorknob.
Just like that.
Tightens hand, opens door, and then pulls back. Using, well, we have a robot with omnidirectional mobility, which makes this possible. Releases doorknob.
And walks out the door.
Next week, we'll be spreading the word with a look at computer languages, speech synthesis, and the teaching of electronics. So until then, bye-bye.